Good evening, good morning, good afternoon. Thank you very much for coming to the webinar, Integrated Lithium Niobate Photonics by Professor Marco Lonca from Harvard University. Professor Lonca is Zinsai Lin Professor of Electrical Engineering at Harvard's John A. Paulson School of Engineering and Applied Sciences, CIS, as well as Harvard College Professor. He received his diploma from University of Belgrade in 1997 and his PhD from Caltech in 2003 with Alex Scherer, both in electrical engineering. After completing his postdoc studies at Harvard with Professor Federico Capasso, he joined CIS faculty in 2006. He is an expert in nanophotonics and nanofabrication, and his current research interests include quantum and nonlinear nanophotonics, quantum optomechanics, and nanofabrication. He has received NSF Career Award in 2009 and Sloan Fellowship in 2010. In recognition of his teaching activities, he has been awarded Levinson Prize for Excellence in Undergraduate Teaching 2012 and has been named Harvard College Professor in 2017. Professor Lonca is Fellow of Optical Society of America and Senior Member of IEEE and SPIE. He is co-founder of Hyperlight Corporation, VC-backed startup commercializing lithium niobate technology developed in his lab. Okay, Professor Lonca.
Thank you so much, Keisuke, for invitation and a kind introduction, and thank you all participants in spending some time this evening with us. So I'd like to share some, actually, is my Zoom bar on top of my title, or can you see my Zoom bar? No.
Zoom?
Can you see my title properly?
Yes.
Okay, okay. And my screen.
Yes.
Something is covering it. That's why I was asking. Okay. Yes. Apologies for that. Yeah. So I'm delighted to share with you some of our work over the last few years in the field of integrated lithium niobate photonics. And also, if you're interested in this topic, I encourage you to check out this review that was recently published in Advanced Optics and Photonics that kind of covers on about 100 pages or so the recent developments in this field from the community. Probably this audience is very well familiar with lithium niobate and its excellent material properties, which include basically pretty high refractive index of 2.2, which is good to realize optical waveguides with high confinement optical waveguides. Most importantly, I would say, is large second-order nonlinearity that manifests itself as a very strong electro-optic effect that allows us to change refractive index of lithium niobate by applying electrical voltages, or on the other hand, is needed for efficient three-wave mixing for, let's say, a frequency conversion. I'll talk a little bit about this in this presentation as well. Lithium niobate is wide transparency window, and in my lab, we have made devices that operate from about blue to 2 to 3 microns, but in principle, we want to go to mid-infrared and down to even kind of towards UV, violet for sure, towards UV as well. And also has large piezoelectric response, which is of interest for acoustic devices, which are also well-known type of devices in traditional lithium niobate, but also in integrated thin film lithium niobate, though I will not have time to talk about this work in this presentation. Because of these nice properties, as I mentioned, this community is probably familiar with the fact that lithium niobate has been widely used in optical communications. It's often referred to as a workhorse optoelectronics. And in particular, lithium niobate modulator, traditional modulator, that's the one depicted here, have found application long-haul telecommunication, wireless communication, radio over fiber types of application, and earlier also in optical interconnects and data centers. though it's, other type of material platforms have actually perhaps dominated this field. Lithium niobate is widely used in quantum optics, and it's a field that's of interest to my research group, so I mention it here. Here, for example, lithium niobate waveguides that are used for photon pair generation, periodically pulled lithium niobate devices used for quantum frequency conversion, to go from 900 nanometer wavelength to telecom wavelength. And more recently, lithium niobate devices, in particular phase modulators, have been proposed as gates to perform photonic quantum computing operations in optical domain, but in frequency domain of photon, basically. So I'll briefly touch upon this later as well. These traditional devices basically rely on largely, I refer to this as a bulk crystal type devices, though in reality they're actually waveguides that are defined by in diffusion or proton exchange process. So basically what you have is bulk crystal of lithium niobate, and then locally refractive index is raised by, let's say, in diffusion of another material, titanium, for example, and this forms an optical waveguide. These waveguides are large, so then when you want to make electro-optic modulator, for example, these two waveguides could be arms of Mach-Zehnder interferometer. Electrodes that you use to make modulator need to be placed relatively far apart from these optical waveguides, not to introduce additional losses. This kind of distance separation results in large drive voltages. Low index contrast to these type of devices also prevents us to make sharp turn and kind of achieve high integration in this platform. And another thing is due to epsilon of lithium niobate being quite large, microwave signals typically propagate much slower than optical signals, so phase and group velocity matching in this structure is challenging, which is why people often introduce this additional spacer layer of silicon dioxide to match these group and phase velocities, which in turn results in even worse electro-optic efficiency of this process. Nonetheless, these devices are really like state-of-the-art, I would say, in the quality of optical signal that can be generated from electrical signal. Relatively recently, what has happened is that these so-called thin film lithium niobate structures have become available. So basically, here I'm showing cartoon of a cross-section of thin film, or I'll refer to this interchangeably, thin film lithium niobate modulator or integrated lithium niobate modulator. Basically, what you have is a blue layer of lithium niobate that has roughly thickness of 0.5 micron, and that sits on about 2 to 5 microns of silicon dioxide on top of silicon handle, though the substrate can be anything really. It can be quartz, sapphire, many other substrates can be demonstrated. These wafers at the moment we purchased from a company in China, NanoLM. And then what one can do is actually you can use reactive ion etching techniques and nanostructuring to realize waveguides. So here waveguides, as shown in this scanning electron microscopy image here, waveguides are realized by partially etching about 600 nanometers thick layer of lithium niobate, and then cladding it again with oxide on top, and before that placing electrodes from gold electrodes on either side of this waveguide. Separation between these electrodes in this picture is on the order of 5 to 7 microns. So just gives you an idea of scale. This actually has much better optical confinement and much better overlap between optical and RF fields, which allows you to have very high electro-optic efficiency. And therefore performance of these drive voltages, or as we call them VPI in this business, VPI voltage is required to kind of change the phase of one of these waveguides in Mach-Zehnder interferometer out of phase with respect to the other waveguide, are low, significantly lower than in the case of these conventional devices. Another nice feature is that due to the structure of lithium niobate and oxide, which is kind of complementary to this structure of oxide on lithium niobate, allows us to control phase and group velocities, phase velocity of RF, which allow us to match phase velocity of RF with the group velocity of optical signal, which allows us to increase the bandwidth of modulators. We have measured in this paper, I'm showing this on the next slide, bandwidth above 100 gigahertz, but collaborators and community has also demonstrated bandwidths exceeding 500 gigahertz even. And so one kind of important, I would say, development in this field that came out of our group now 4 years ago already is demonstration of electro-optic modulator using this thin film platform. Oops, apologies. Using this thin film platform that, in addition to very low Vpi, as shown here, of 1.4 volts for 2 centimeter device, and very high bandwidth that exceeds 100 gigahertz, we were able to demonstrate data transmission through these devices on the order of 210 gigabits per second. This is somewhat old results, and we're going to go into details of it, but basically, this shows here is the data rate of about 70 gigabits per second when modulator is driven with as little as 60 millivolts of peak-to-peak drive. So this allows basically this really low drive voltage reduces power consumption, but also perhaps even more importantly allows you to drive these modulators directly from using CMOS signals, which eliminates the need for RF amplifiers, which is great savings in both cost, energy, and also space. And here we compare this type of lithium niobate modulators to, let's say, silicon photonics modulator in context of phase shifter loss, basically the loss of the modulator and the drive voltage. And you see that, for example, in materials that are not good electro-optic materials like silicon, you see the trade-off. If you want to have very low drive voltage, you pick up a lot of loss. Meanwhile, lithium niobate, this trade-off almost doesn't exist. Basically, you can have very low voltage without incurring significant loss, optical loss. And another kind of nice feature is that these devices that I showed you, they are all realized using conventional planar fabrication technologies. So here we are showing wafer, I believe this is 4-inch wafer. These wafers now come in 6-inch size as well. And you can use lithography plus etching to realize large number of devices. Each of these little chiplets here is one modulator and a bunch of other kind of functionalities. And when you compare this device, for example, to conventional Fujitsu modulator, you can see that devices are significantly smaller. And not only that devices are smaller and therefore and also more efficient and high performance, but this allows you to integrate additional functionalities, as you will see, on lithium niobate chip, which further enables a wide range of applications. I should point out that this wafer comes from the Hyperlight. It's a company based in Cambridge, in Harvard Square, that is commercializing this technology and basically commercializing modulators and many other components, as you will see. So in this talk, I would like to tell you a little bit about this integration and types of devices that we can make. Oops, all right, I guess antivirus wants to scan my disk now. The devices like two types of devices I want to focus on this presentation. The first part of the talk, I'll talk a little bit about sources of femtosecond pulses on chip using electro-optic effect and lithium niobate in particular. Basically, the frequency comb sources, and I'll talk how we can generate frequency combs, a few different strategies, and how we can manipulate the spectrum of frequency combs. And it's kind of broadly falls in category of applications in RF photonics. In the second part of the talk, I will talk a little bit about maybe it's kind of physics driven, but this photonic molecule concept of two coupled ring resonators that also has many interesting applications, including frequency comb generation that I'll show, as well as application in the frequency domain quantum computing and microwave optical transduction, as illustrated by this picture. So first part. So as I mentioned, it's motivated by realizing integrated sources of short pulses. And these, short pulses or frequency combs have a wide range of application, and I'm naming some here. For example, in sensing, chemical imaging, in ranging, LiDAR applications, atomic clock signal distribution, Also, they can be used in quantum communication as a time multiplex single photon sources, and so on and so forth. Microwave generation is another big one. And typically they have relied on tabletop bulky components, but most notably TISAF lasers, recently also fiber lasers, that produce short optical pulses. That in time domain basically look like this. Pulse envelope is on the order of, in our case, few hundred femtoseconds, as you will see. So it can be significant. It can be shorter as well as longer. And in frequency domain, basically these kind of pulses form a frequency comb, which is also of interest. This kind of frequency domain picture is also of relevance for wide range application that I mentioned. Big deal about in frequency comb business is stabilizing the comb, which means stabilizing, locking the pulse envelope with a kind of the signal itself, optical signal itself. And for that, typically what's needed is detect this carrier envelope offset frequency, FCO, which actually requires second order nonlinearity like the one provided by Lithium Niobate. So the goal of our research is actually to eventually provide complete solution to stable, broad frequency comms that could be also very small and portable. When it comes to the integrated optics solutions to frequency comb generation, there are roughly two approaches. One is based on mode-locked lasers, and then pulses from these mode-locked lasers are typically directed to some sort of nonlinear medium for pulse compression and spectrum broadening, for example. And this can be done in, let's say, dispersion engineered waveguide, in optical fiber, and so on and so forth. Another approach uses continuous wave lasers that are driving ring resonators with third order nonlinearity. Both of these actually long waveguide and a ring resonator have third order nonlinearity. And due to process of cascaded four-way mixing, what happens is these kind of pulses are converted, CW light is converted into optical pulses with repetition rate that's the same as free spectral range of the resonator. And in the output, they look basically as a frequency comb. So originally, we actually have demonstrated both of these functionalities, as I'll show you in Lithium Niobate. But originally, one of the first motivation for our Lithium Niobate platform was indeed to realize comb using Kerr effect, then to broaden the comb using this broadening, and eventually to do second harmonic generation to lock the comb. First, we wanted to demonstrate that the high quality factor lithium niobate resonators are possible, because this is one of the precursors to reduce the threshold for frequency comb generation. So here's some already 5 years old work that shows that ultra high quality factor lithium niobate cavities with Qs about 10 million in telecom wavelength can be done. By the way, we have recent development where we measured material limitations of this thin film lithium niobate, and we predict it's on the order of 200 million. And this is some work in collaboration to this Kimber's group in Lausanne. So basically, this value that we measure is limited by our fabrication of the material. So there's a lot of opportunity that could be unlocked if we can further increase this quality factor. This quality factor of 10 million, by the way, translates to losses, waveguide losses about 3 dB per meter, which puts this integrated thin film lithium niobate platform kind of as up as one of the lowest loss integrated photonics platform. And importantly, we have demonstrated this in both telecom and visible wavelength range. When you go to short wavelengths, there's some other issues with lithium niobate, like a photorefractive effect that I'm not going to talk a lot about, but I'm happy to answer questions. By the way, if there's any questions throughout the presentation, please feel free to interrupt me, or at the end of the presentation, either way is fine. And then with these high Q resonators, we have actually demonstrated first lithium niobate based curved frequency combs, as shown here. In particular, actually, so in this chip that we fabricated, we have a ring resonator that's coupled to optical waveguides. We come with CW light, and this ring actually gives us frequency comb, and this is the spectrum of the frequency comb. For the experts, these combs were actually not mode locked, and these additional peaks correspond to Raman lines, which we also studied, and I'm not referencing that work here, but basically because of this Raman scattering process in this crystalline material like lithium niobate, actually turns out these combs were not locked, which is a problem for applications. Another thing that we demonstrated here, we integrated this comb source with tunable modulators, switch channel drop filter / modulator. So this is lithium niobate ring that basically can be tuned to pick either any of these lines that is generated and drop it into this waveguide here, as shown here. And this is of interest for down the road, would be of interest for highly multiplex optical communications. Then you could envision coming with one color of light, generate broad spectrum, daisy chain a bunch of these rings, each of them drops one channel, one color of light into waveguide, and then you can follow this up with a modulator. And then in the end, so you multiplex everything and you can have very high aggregate rates. The problem with Kirk frequency combs that I showed is actually still not only lithium niobate, but in all essentially all material platforms that have been explored is low comb efficiency. So basically only a fraction, like maybe % or so of CW light gets converted into frequency comb. On the other hand, mode-locked lasers suffer from issues with optical alignments and repetition rate noise. And so, which then, poses an interesting question: why not look back at electro-optic combs? And so, those of you who maybe are interested in this field, you may know that electro-optic frequency comb sort generators were among the first ones that were proposed, but then due to rapid development of mode-locked lasers, particularly TISAF, they were somewhat abandoned. But I think now with this development, if integrated lithium niobate photonics, we actually think that this can make significant advancements in this technology. And electro-optic combs basically take advantage, as I said, of this ability to modulate light very efficiently with very high speed in thin film lithium niobate modulator. Basically, we can carve pulses just by optical modulation. There is no mode locking that's required. There is no threshold. Basically, once we turn RF source on, we get a comb. And as you will see, a pump to comb efficiency can be very large, in the order of 20 to 30%. So next, I would like to discuss a few different electro-optic frequency combs we looked at. And in contrast to curve frequency combs that I discussed so far, that rely on third order nonlinearity, electro-optic frequency combs rely on second order nonlinearity of lithium niobate. And basically, the simplest way to think about this is actually not amplitude modulator, as I mentioned in the previous slide, but phase modulator. So you take lithium niobate, apply electrical RF signal, generate sidebands, and then you drive harder this phase modulator, generate more sidebands, and that's your comb. The lower the V pi of the modulator, the more comb lines you can get. And indeed, and that has been done with conventional lithium niobate modulators, of course. And in this work referenced here, we have demonstrated this with thin film lithium niobate as well. Advantage of our approach was that V pi was low, and therefore we could generate more comb lines than what you can typically do in a conventional device. One drawback of this approach was, as you can see here, that this comb wasn't flat. And that depending on application, it can be a problem or not an issue at all. For envisioned application in telecom, where each of these comb lines that we generate would be optical carrier, actually, it's not good that some of these carriers are like 15 dB or less than suppressed than their neighbors. So and for application in space spectroscopy and many others, actually, we would want to have these comb teeth have the same strength. And so fortunately, the community has actually recognized this shortcoming and proposed solutions. And here is 3 examples of the solution that all rely on cascading basically several modulators, daisy chain several modulators. For example, in this work by Scott Diddams and Scott Pupp's work, they take intensity modulator follow it up with two-phase modulator, and by controlling the RF, controlling the phase difference, you can actually get flat spectrum. In this case, they also followed up this frequency comb, essentially pulse source, with highly nonlinear fiber and some pulse shaper that allows you to actually broaden the comb and generate and make it more dense and very, very flat. In this work, they used 3 different modulators that all were 3 different chips, but not chips, 2 different like old school modulators, which introduces high loss when you have high insertion loss of each component, which is what drives the need for this EDFA here and a few other amplifiers along the way. And the same is true for other demonstrations from here. So we were, we wanted to see, can we actually integrate most of these components on the same chip, including modulators and nonlinear dispersion element for pulse compression, so that we can have chip scale femtosecond source or chip scale flat comp, basically. And here's the solution. So basically, this is a chip that was developed in collaboration with Hyperlight that consists, as shown in this cartoon, of 1 amplitude modulator and a kind of special type of phase modulator. It's essentially both modulators operating ground signal ground configuration. And this phase modulator basically light is inserted from this end, goes through Mach Zehnder interferometer, comes back here, goes through 1 arm of phase modulator, and then it loops back and goes to the other arm of phase modulator. Okay, so in this case, we can actually make the effective length of the phase modulator twice the physical length, which reduces the VPi, which is nice. And so this is a characterization setup that shows RF electrodes. One is used for the drive, the other one is used to terminate the device. And here's DFB laser that we obtained from Freedom Photonics collaborators. And these devices actually, when combined with, they actually directly but coupled to lithium niobate chip for this waveguide. So this makes a very compact device. And here is experimental data that shows the same device driven at 10 gigahertz and 30 gigahertz. We can get 90 that is 67 comb lines, and comb spectrum is very flat. In both cases, VPi is very low. And also the flat comb being flat can be actually nicely seen from in linear scale, whereas this is here log scale. So if you show this comb spectrum linear scale, you see that these linear comb lines, which are the ones we would use, have actually very, very flat comb spectrum. Total comb power is roughly 25% of pump, CW pump, which is pretty good conversion efficiency. And also pump per comb line is pretty high. So we were quite excited about this. I should point out this is developed in the context of Lumos program, DARPA Lumos program. And in addition to Hyperlight and Freedom Photonics, we work with PSI, with Ed Ackerman and team, in looking at the application of this thing in RF photonics, and also Andreas Behling in Virginia, who is integrating detectors. I won't have a chance to talk about this today, but that's also another exciting development. When you look in time domain, take this comb spectrum and look at the time domain using autocorrelator, you see actually we get very nice pulses of 500 femtoseconds. So basically we start with CW laser, apply RF, and generate 500 femtosecond pulses. In this case, what I didn't tell you is that actually it's a little bit of a cheat, because at the output of this lithium niobate waveguide, we have about 100 meters of fiber that is used to compress the pulse, actually. But recently, we have looked into replacing this 100-meter fiber with this kind of dispersion element, which is basically chirped grating. Consists of a lithium niobate waveguide that has side edge gratings, and periodicity is chirped. So this is realizing on the same chip, essentially. And these devices, I'm not going to go into details. In about 2 millimeter device, we can get the same amount of dispersion as in 100 meters of fiber. And importantly, the loss of this loss is very, very low. It's 0.33 dB per centimeter. And as I mentioned, the device is only 2 millimeters long. So this is actually really low loss. Almost we get, and the device works in reflection. So we get 99.5% reflectivity of light. So basically, broad optical pulse comes in for several picoseconds and gets pushed back and compressed, and we get about 500 femtosecond pulse. So this is experimental data, shows pulse that emerges from this device and comb spectrum. And also now we have, again, with collaboration with Hyperlight, we are now integrating all of these components on the same chip. So here is, this part here is comb source or amplitude and phase modulator. And then this is this kind of pulse compressor that I showed you, all on the same chip. So now we don't need the fiber, basically output of this pulse compressor as these femtosecond pulses. Here you see two different actually comb sources, which is of interest for applications like in dual comb spectroscopy that we are also exploring. Ultimate goal is to integrate lasers on the same lithium niobate platform, so we don't have to use optical setups to bring the light in. And we have demonstrated this recently. So basically what we use, it's a flip chip bond distributed feedback laser on a prefabricated lithium niobate chip. So basically here's top view. So this is all lithium niobate with modulators realized. And then in one part of the chip, we etch trench in which then we bond the DFB laser. And this is all done with passive alignment. We are able to get about 60 milliwatts of light. The laser has about 200 milliwatts, actually 180 milliwatts or so. We're able to get about 60 milliwatts in waveguide, and after we are done with everything with modulator, we get about 25 milliwatts of power. Nice thing is that this is integrated with high-speed modulator. So basically we have DFB source and amplitude modulator here that can be run at, we demonstrate 50 gigahertz here. Theory says that this should operate up to 100 gigahertz, but this bandwidth was limited by a photodiode that has a roll-off at about 40 gig. So the goal is now to take this and combine it with basically our frequency comb source. So we can have a chip that all you need to apply is DC power for DFB laser and RF power for modulators, and outcome 500 femtosecond pulses, or outcome broad frequency comb. So what we have demonstrated too, but haven't combined with this platform, is actually frequency comb stabilization. I mentioned the goal is to make broad comb so that you can take to detect carrier envelope offset and make sure that the comb itself is stabilized, so that the envelope and actual optical signals don't slip. And this is typically done by taking Broadcom spectrum and doubling one wavelength and comparing it to the other, doubling one frequency, comparing it to another, to the frequency in the other end of the spectrum. And the beat note generates essentially carrier envelope offset frequency. This process of second harmonic generation is conventionally done with lithium niobate modulators. So our idea was, well, let's combine all of these things now on the same lithium niobate chip. Normally, when people do this, they first broaden the pulse using, as I showed in one of the opening slides, using dispersion engineering waveguide. And then after the pulse broadening, they actually use second harmonic generation to double the spectrum. In our case, actually, we can do all of this in a simple lithium niobate waveguide. We hit the lithium niobate waveguide with the pulse, and then as pulse propagates, first we see second harmonic generation, and then as pulse propagates further, we see supercontinuum generation. And if supercontinuum is broad enough to overlap with second harmonic, by detecting basically this part of the spectrum, we can see the beat note carrier envelope offset frequency can be detected and whole system stabilized. So this shows broad supercontinuum generation lithium niobate waveguide of about 2.6 octaves, and this shows that this principle worked. We were able to detect carrier envelope offset frequency. In this case, this was mode locked benchtop laser, I believe it was fiber laser. It was done in collaboration with Alex Gaeta's group. So basically we used integrated chip to stabilize big lasers. In reality, what we would like to do, to use this same waveguide integrated on our comb source to stabilize that comb source. The issue is that our comb source doesn't produce enough power to generate supercontinuum that's as broad as we need. However, nice thing about lithium niobate is that nonlinearity of this waveguide can be engineered. And this can be done by periodic polling. So it's some work we've been doing in Martin Fair, and I'm not going to go into details here, but basically what we can show we can do by periodically polling lithium niobate, we can increase effective third order nonlinearity of lithium niobate by 2 orders of magnitude, essentially, which are compared to material like third order nonlinearity, which allows us to generate a broad supercontinuous spectrum with picojoules of power, which is getting very close to the powers we're generating from our frequency combs. So by increasing the power of the comb a little bit and improving this nonlinear process, we're fairly confident that we will be able to not only generate comb and then broaden it, but also lock it. And this would be like really nice chip bail frequency comb source. Another thing that we can do with a frequency comb, and something is important, but this is a little bit out of place, but maybe ignore this cartoon here, is that we can shift the spectrum of the whole comb packet that we generate. In this case, actually, results I'm going to show you is for slightly different line of work, where we are using phase modulator to change the color and bandwidth of single photons. So all the experimental data I already show are done on single photon pulses, but in principle, the same thing can be done on classical pulses like the ones I was discussing so far. So the way this works, and so the why we are interested in this is basically you have some pulse packet at one center frequency, and you want to shift the center frequency left to right, or we may want to broaden it or control its bandwidth. And this is super important for quantum applications. I'm not going to go into details. This is kind of illustrated here. I'm just going to show the concept real quick. And the basic idea is relatively simple. If I have electromagnetic wave where phase can be modulated in time linearly, that is basically equivalent to adding frequency shift. So this is called spectral shearing. The way we do this is take phase modulator, apply RF drive, and then time our optical pulses to hit, to be kind of synchronized with the rising edge of simple RF drive, harmonic RF drive, in which case we get frequency upshift, or if it's synchronized with a trailing edge, we get frequency downshift. And we showed that using this on single photon pulses, we actually can generate move comb by about plus minus 600 gigahertz. So we generate comb at, let's say, 1550, and we can move it plus minus 600 gigahertz. So this is very useful and for quantum applications where we need to be correcting for some inhomogeneous broadening of quantum emitters on the order of 50 gigahertz or less, but could be of interest for classical applications as well. And finally, I want to say that another type of electro-optic frequency combs that we considered in our lab are resonator-based electro-optic frequency combs. So frequency combs that show you, electro-optic frequency combs that show you so far are, I said, are based on phase modulation. And then we made this a little more complex. We took one amplitude modulator and kind of one phase modulator, plus this chirped gradient for compression. But in reality, the process can be made a lot more efficient if you take phase modulator and put it in an optical cavity. Your free spectral range of this cavity is the same as modulation frequency that you're applying, RF frequency. This process of sideband generation is resonant with the cavity, and thus it's enhanced. And then you need less optical power or less RF power to generate very broad comb. That has been done before several times. Using discrete component lithium niobate or lithium tantalate in this case lithium niobate modulator. And in our approach, what we did, we took our chip scale ring resonator, similar to the one I showed you at the beginning, put electrodes, essentially phase modulator, combine it, and then couple it with optical waveguide. And by driving these electrodes with about 10, 20, 30 gigahertz RF fields, we could generate broad comb spectrum as shown here. So this comb was pumped at about at this wavelength here, about 1600, and we applied RF signal, and we were able to get this nice broad comb. The issue here is that this comb is not very efficient. In fact, if I were to show you the pump on the same scale, you would see that efficiency is below 1% here. It's like 0.3% or so. But comb spectrum is much broader than what we showed you before. And the reason why this comb is not actually very efficient, and there is a lot of interesting physics that we explored and published 3 papers on this, like this process of comb generation in resonator can be seen as a process of random walk of a photon in frequency domain or photon It's analogous actually also in tight binding schemes, having an electron in a kind of one-dimensional crystal, sort of like simple solid-state physics. It's pretty much the same formalism. The reason why the comb cannot be broader is actually quite interesting. So in blue, I'm showing you the transmission spectrum of the resonator with RF is off. So this is typical resonance dip that you see. One of the resonances, there's many of these resonances that I'm only showing one. The typical resonance dip that corresponds to ring resonator, shown here. Once and in this case, we carefully designed coupling between ring and a waveguide, so the ring is so-called critically coupled. So basically, transmission is 0 on resonance and 1 on off resonance. And in order to do that, you match losses of the ring resonators to the coupling loss. So now, what happens when you turn RF on? Because RF couples nearby resonances. So essentially, if I put light in this resonance with RF on, now photon can jump to this resonance, can jump to that resonance. Effectively, I'm using additional loss channel for the resonator, which means the resonator immediately becomes undercoupled. And the more RF I apply, the more loss I have, the more undercoupled it gets. So with strong RF, I have this red line. So there's this trade-off. I want to apply a lot of RF to get broad comb, but as I apply a lot of RF, no light goes in. And so that was a problem, actually, that prevented us to make this really broad comb. And a student of mine came up with a very elegant solution to this problem. This is a problem again. And without going into a lot of details, he realized that the trick is to make sure that resonator is critically coupled at a pump frequency when RF is on. So he was able to achieve this by introducing this additional ring resonator, thus forming what we refer to as well as community broadly photonic molecule, and more about this I'll tell you in a few slides. So these coupled ring resonators, by controlling carefully coupling rates in different loss channels, you can actually be in a situation that you get maximum power transfer from the pump into this comb ring when RF is on. And using this experimental data, he was able to show that compared to single ring resonator comb, he can get much broader spectrum with about 2 orders of magnitude more efficient comb generation and about 30% efficiency, which is like unprecedented for resonator-based comb. As I mentioned, it's on the order of few percent, unless you're operating in so-called dark solid mode, but then bandwidth of those dark solid combs is not very large. So this is super exciting, and also this kind of produces pulses on the order of 500 frames per second, and we also use this now actually quite routinely in our lab as kind of benchtop comb source for some nonlinear experiments. This concept of coupled ring resonators, as I mentioned, we refer to as photonic molecule concept, and I would like to tell you a little bit more about this and some other applications of this concept in a kind of second part of the talk, which is going to be a little shorter. So I already told you that if I have, and you probably know that already, if I have single ring resonator coupled to single waveguide, this is transmission spectrum that you typically expect to see. These are individual resonances. If I couple now 2 ring resonators, each of these resonances splits in 2, forms doublet. And if these 2 resonators are identical, actually, this is kind of an interesting scenario. In our comb source, the 2 resonators were not identical, but it was also fine. But basically, what happens is you form this doublet, and you can think about this as a coupled quantum well. And what's really interesting in our case is that in analogy to coupled quantum well, where you apply, if I have 2 levels for electron, I can apply optical signal to make transition from one level to another. In our photonic molecule, I have 2 optical levels, 2 optical modes, and I can apply RF signal to drive transition from one mode to another. That is to drive light from this resonance to this resonance and back. And the device that we are looking at is shown here. It looks slightly different than the photonic molecule I showed you previously in the case of comb generator. But this device actually some very interesting properties that I would like to share with you in the next few slides. So this was originally driven by some interesting physics, but then actually there's some quite relevant applications in quantum technology, which is why we are looking into this in the first place. Indeed, this behaves as a molecule because, like, if I had that, or atom, or molecule, or quantum well, actual quantum well, you know, you're familiar with DC Stark effect. I apply DC bias, and I can basically tilt the potential, and I can split these resonances. The same is true, as you can see, for our optical molecule, photonic molecule. Here, what we're doing, I apply DC bias to lithium niobate ring resonators. And what is that going to do is going to induce splitting between these two resonances. And the splitting, as you can see, goes from about 7 gigahertz to about 18 gigahertz. Also, I can have AC Stark effect, which is I can apply RF field in resonance with this splitting, either original splitting or splitting due to DC Stark effect. And what that does drives Rabi rotations in between these two optical levels. So another way to think about this is I put light in one of these resonances, apply RF field, and then light goes here, RF field is on, light goes here, 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 and so on and so forth. And you see this shows basically transmission through this device, like how light is going from one. Light. We put light in this resonator, turn it off, and apply RF, and you see how light is going from one resonance to another. So why we are interested in this, or we were interested in this originally, is because this, in principle, we calculated could be extremely efficient single-sided modulator. Basically, what you could do, you could put light in this frequency, apply RF signal, go to this mode, this optical mode, rather put light here and up here, and then you turn RF off, and now light stays here. So essentially, in the context of Rabi rotations, this would be like pi pulse, as they call it. But unfortunately, I mean, that works. We demonstrated that actually. But the problem is that you need to have pulsed RF, and these signals are, you know, about 10 gigahertz. Sometimes we go up to 30, and then if I want to have pulsed RF source at about 10 gig, that means bandwidth needs to be much larger, and that just becomes really expensive, and we actually don't have one. But my student actually looked very carefully into this, and he realized very interesting relationship between different rates that are kind of participating in this process. The rates of different processes that participate in this process. So the same topology, same two ring resonators with two electrodes, RF electrodes. Again, put light in one resonator, apply RF, and now we want to get light out of this resonance. And he found out that if you precisely control this coupling rate, this RF-induced Rabi rate, and this rate, you can find regime, but not all of these rates are the same, it turns out. We refer to this as a critical, a generalized critical coupling condition. The process interrupts itself. Essentially, light goes, we put light here, light comes here and leaves the system. So Rabi rotation cycle gets interrupted, which is exactly what you have in single-sided modulator. So here is single-sided modulator experimental data. We make two ring resonators that have splitting of 12 gigahertz. We put light originally in one of the resonances, turn RF on, and RF is on all the time. But if you dial in appropriate amount of RF power, all of the light from this resonance ends up being here with 99% efficiency. And what's really interesting, process is reversible. So if I put light at this resonance and apply RF, all the lights end up here, as shown here. So you can use this to swap two channels. So you can think about it as a single-sided modulator. You can think about it as a frequency shifter. What we did, we had a laser, CW or pulse laser source, doesn't matter, at this frequency, applied RF and got laser light at this frequency. And this is, you know, what we refer to as frequency shifter. And when you compare this, I'm going to start using language of quantum optics. What I did here, this is analogous to, let's say, if instead of frequency of the photon, I was looking at polarization of the photon, I went from T polarized light to TM polarized light, which is what I can do with the waveplate. If I'm talking about spatial domain encoding of a photon, this is equivalent of putting photon in one waveguide and then using directional clockwork to get photon in the other waveguide. And this is used to encode qubits in quantum photonics. Another component that's often used in this business is also beam splitter, which is in context of spatial encoding of the photonic qubit is just beam splitter. In frequency domain, beam splitter would be a device that would take your optical pulse, take signal and one wave frequency. You go to this frequency beam splitter and you get light to emerge is 50-50 split between two different frequencies. And in reality, the same device, this kind of photonic molecule, gives you exactly the same, can perform this functionality, this functionality. Some of you may be actually familiar with the single subwave modulation using IQ modulator. That process inherently has 6 dB loss by design, or I think 6 dB. Our approach, like by design, inherent loss is 0 dB. There's of course the losses with fabrication and whatnot, but it's it's quite interesting concept, I think. Going back to beam splitter, basically we have frequency shifter. In this case, the device with splitting was 30 gig, not 12. And so what this shows is how much light we have in one optical resonance versus another optical resonance as we are changing microwave power. So originally I put all the light at, let's say, in one optical mode, and I'm slowly dialing up RF power. And you see at some point I have 50-50 split between the two resonances. And this is when I perform frequency shifter functionality. And then I keep dialing up the power and then, frequency beam splitter, and I keep dialing up the power. And now all of the light is moved to the second resonance, and this is like frequency shifter functionality. So what is also super interesting, but we haven't demonstrated it experimentally, but we did demonstrate theoretically, is that actually by controlling the phase, also microwave power and phase, microwave phase, we can actually perform unitary transformation on a photon. So basically, we can put single photon at omega 1, and we can fix its phase and frequency after this device, which is enough to demonstrate so-called single qubit operation on a photon. And so next thing will be to demonstrate 2 qubit operations, 2 qubit gates, which is something we're working on right now. If you're interested just in the single subwave modulation, let's say, okay, so now you believe us, we can do like single subwave modulation or frequency shifting by the amount of original splitting between two resonators, let's say 12 gig, or in this case 30 gig. But what if I want to do more? If I have light in one frequency, I want to shift, let's say 120 gigahertz, not 30 gigahertz. Well, I could make the system that has 120 gig splitting, but then I need to use 120 gig RF drive, which are quite pricey. Or I can do something else. I can come up with a process that's cascaded. I have used a bunch of resonances, each separated by 30 gig, but I cascade. I go from one resonance to nearby, to nearby, to nearby, to nearby, and then take my photon out. So if I do it 4 times, I have 120 gig frequency shift. And the device that does that is shown here. It's actually quite complex now. We have 3 rings. The role of this, so if I don't have this ring, what happens? I have just frequency comb. Like these 2 rings form high power frequency comb I showed you. So this process here I'm showing would cascade in perpetuity, right? It would go, it wouldn't stop after 4 cascades, it would just continue. But if you bring this ring here, I use it to break the symmetry of the system, or to break this periodicity. So what this ring does, I tune the resonance of this ring to the resonance of this ring. Basically, this resonance is tuned to this resonance to this resonance, and they are strongly coupled. They introduce splitting. And this splitting breaks the periodicity. So now light cannot go this way because it's a mirror, essentially. Light can only go this way, and then it has to get out, cannot go forward because there's no periodicity anymore. And indeed, we fabricated this, and indeed it works as promised. We were able to shift here with maybe 80% efficiency, not 99% efficiency. We were able to put light at this resonance, and then applying 30 gigahertz drive, we could shift signal by 120 gigahertz. By reducing the losses, improving coupling and whatnot, we could eliminate these kind of intermediate steps. So it's kind of cute to see these intermediate steps as well in the process. and get most of the light, actually 90% plus light exiting this frequency. So that is kind of along the line of frequency control of light using these photonic molecule, or in this case is like, you know, photonic molecule with 3 photonic atoms, if you will. But before I maybe wrap up, I want to introduce one more application of this process, which is in microwave optical transduction. So maybe I'll go back to this slide real quick and just tell you what we're trying to do here. So the question was, what is the ultimate, how much, I show you, for example, that, I don't know, with 10 milliwatts of RF power, I can take all optical light from this resonance and put it in this resonance. But I can ask an additional question, how, like, can I actually, how many photons can I move from this resonance, optical photons, to this resonance, if I have only one microwave photon at 7 gigahertz? So the question is, can I make extremely efficient modulator that takes only one RF photon and modulates optical signal? What one RF photon would take one optical photon from this resonance and put it here. It's like essentially a three-way mixing process. And why I care about it is because if I can do this in a coherent way, then I can potentially encode any transfer information carried by this microwave photon, maybe it's in superposition state with some other microwave photon, and transfer it to optical carrier. And then I can send this optical carrier over optical fiber over a long distance. And on the other end, I can kind of detect this. So basically what I want to do RF photonics at single microwave photon level. And why is this needed? Well, it's needed in application like superconducting quantum computing. For example, if I have a superconducting quantum computer that sits, you know, I have these qubits that sit in the illusion refrigerators like these guys, and I'm not going to go into details now. The superconducting qubit operate at microwave frequencies, and this operates at 10 millikelvin, and the illusion refrigerator, which is actually one of the systems we have in the lab. But now if I want to make down the road distributed quantum computational system, I would want to connect to superconducting quantum computers. And I cannot do this using microwave signals. Maybe just take a look at the bottom, in the interest of time, the bottom picture. If I want to connect to the illusion refrigerator with superconducting quantum computer inside, using microwave signal, that's not possible because microwave signal will decay very quickly over, let's say 7 gigahertz signal over some RF cable. And more importantly, noise, thermal noise, once you get to room temperature, once you're out of the fridge, thermal noise will kill you. So what we and others in the community are doing is actually making these extremely efficient modulators that can take information from single microwave photon, encode it on single optical photon, send optical photon along fiber over long distance. On the other end, receive that optical photon and kind of match the receiver in a way, and go back to microwave domain. And it turns out that our coupled photonic molecules are almost ideally suited for this task, actually, amongst various platforms. And so maybe just the last couple of slides, I want to show you how this looks like. This is still work in progress, so we haven't quite done this at high efficiency yet. But here is 2 ring resonators integrated with superconducting lithium niobium nitride film. This is collaboration actually with Will Oliver and Carl Berger at MIT, and also now with Rigetti Quantum Computing Company. So this is superconducting resonator, no qubit yet. We demonstrated that the process works. I'm not going to go into detail. The efficiency of the process is on the order 10 to the negative 5. Ideally, it should be 100%, should be 1. We are about 5 orders of magnitude off. But the issue here was this process, without boring with detail, was actually limited by many inefficiencies in like delivering light. This is the first time we've done this as a community. Take a light from the fiber, put it in the illusion refrigerator, illuminate this device while trying not to illuminate superconductor, because it doesn't become, it's not superconducting anymore if it absorbs photon, basically. So how much light, the process is more efficient if you have more light, optical photon, but then we have more scattering. So we have, since this work was published, group at Yale demonstrated actually efficiencies, I believe, of 1%, if I'm not mistaken, using the exact same platform, just optimized. And we have experiments underway that we are hoping would hit at least 10%, if not more. And devices that we are hoping will bring us to this, these paperclip cavities, these two-ring resonators that are nested. They have some advantages, but I'm not going to go into detail on that. Maybe at this point, I'll just summarize. So in the first part of the talk, I told you a little bit about generation of femtosecond pulses and control of femtosecond pulses. Like, for example, here's one example, but even though this was from quantum space, how we can move optical pulses left or right after we generate them. And the second half of the talk, I told you a little bit about this concept of photonic molecule that can be used in quantum transduction, briefly touched upon. Broadly, we believe, together with our collaborators, not sure exactly what PSI is not in this thing, but collaborators, Hyperlight, Freedom Photonics, PSI. We believe that this platform of lithium niobate, integrated lithium niobate photonics, could be quite interesting for RF photonics applications. We are integrating lasers with the frequency combs, modulators, multiplexer, detectors, so on and so forth, while also being super excited about applications in integrated quantum photonics, in particular making quantum repeaters, which I haven't talked a lot about, but it's kind of illustrated by some of these slides here. And finally, I'd like to acknowledge current and former students and postdocs in the group listed here. In particular, these are the students who are in my group working on lithium niobate process. We have another branch of research that's focusing on diamond and quantum optics applications with diamond. And those are not listed here. And collaborations from MIT, I mentioned, Carl Bergen with Oliver Dirk and Frank Wong. Modulator work is done in collaboration with Nokia Bell Labs. A lot of comb work with Alex Guetta at Columbia. Periodic couple lithium niobate, essentially all things lithium niobate, started with Marty Fair, who is kind of big boss of what he refers to lithium niobate from the dark ages, the conventional lithium niobate platform. Now we are working on this lithium niobate platform together, as well as Shen Hui Fan and Joe Kahn. Ed Ackerman, Ed Wooten, and Charlie Cox from Photonic Systems Incorporated are kind of partners in this RF photonics application, and Tobias Kippenberg and his team. We have, I mentioned some work on trying to estimate the losses of lithium niobate, which are actually very, very low. And with that, I'd like to stop and thank you for your attention, and happy to take any questions if there's time. I guess I ran a little bit over time. I apologize for that.
Thank you very much for the very exciting talk. Thank you. And we are now open to questions. Please type in the chat or raise your hand. Well, first, there's one question in the chat from Chenglin Xu. The device modulator or EO Combs is quite long in the range of centimeter range. Velocity mismatch must be an issue at high modulation speed. How do you resolve the velocity mismatch problem?
So I'm going to assume that the person who asked this, gentleman who asked this question, is probably familiar with the let's call it old school lithium niobate. Indeed, it's 2 centimeters. We actually made it even longer. It goes back to this, which is really a nice kind of, I wouldn't say, it's really nice consequence of this thin film platform, which is something we didn't consider at the beginning, but came for free, is the fact that this layer of silicon dioxide, thickness of this layer, we choose carefully to basically make sure that we match phase velocity of RF, the group velocity of light, which is, we do. The main issue for us in terms of modulation bandwidth and efficiency is the length of the microwave loss, basically. So we can, from the point of view of group velocity matching, we can make the electrodes really, really long. It's not an issue, many centimeters. But microwave loss actually kills us. Yeah, that's a very good question. This is the problem in old school lithium niobate, not in the new school lithium niobate. Hopefully that answers the question.
Any more questions?
I had a question actually, Professor Lonkar. You were discussing the, sorry, where did I find? Yes, you generated very impressive results. Your octave spanning supercontinuum generation. I was curious, what was the pulse width that as you entered the waveguide there, where you're both doing supercontinuum generation and also second harmonic generation? What was the pulse width that you were able to get such a broad spectrum?
Yeah, so these are short pulses because the pulse energy actually I was combining a bunch of slides just to try to cover as much ground as I can. I want to say this was 120 seconds, maybe a little shorter. These were like really, really short pulses. This was, the measurement was done by Yoshi at Alex Getter's group, so we don't have that tool, so I don't remember exact pulses, but it was shorter than 520 seconds that I was showing here, much shorter.
Okay, so those were was that a
yes.
compressed output of one of your combs, or?
No. So that I wasn't clear. So this result here is supercontinuum source driven by tabletop big like commercial pulse source.
Okay.
We couldn't do it. We would love, the whole idea is to do the same with our source, but we cannot generate this type of energies at the moment, which is why we are hoping to reduce energy requirement by using this periodic polling, as shown, at some wavelength, we can actually do it with like 2 orders of magnitude less energy, but still we need to have shorter pulses. So, we're probably order of magnitude off at the moment to be able to do the same with on-chip source, yes.
Mm-hmm. So maybe a follow-up question. What do you see as the more limiting factor in terms of using your on-chip comb source as the seed for the supercontinuum? Is it pulse energy or is it pulse duration?
It's I would say it's probably pulse duration. It's peak energy essentially, which comes down to pulse duration, because we could in principle always use stronger pulse source. I mean, in lithium niobate waveguides can really take punch. Like we are pushing in resonator routinely, there's like tens of watts of power circulating. And when we generate this comb source, we were using like 180 milliwatts of DFB laser power. So, and we looked into this. If we simply just scale up the power, and you can have some of these DFB lasers like exceeding watts, it wouldn't be there. So I think we need to compress further. That's yeah. Pulse duration, I would say, is the moment for them. Which basically we need to have broader comb in a way, more efficient RF generation, more efficient comb generation using RF, which you can do. For example, lithium niobate on quartz has very low VPI, so for the same RF power drive, we can make much broader comb in principle.
Thanks.
Since you ask, another thing that is interesting is you can, instead of waveguide based broadening, like shown here, what you can do, you can take resonator, not this, like it needs to be much longer. So now you have resonant, and people have done this actually in another platform. So if you match your comb rep rate with free spectral range of this resonator, you can have resonantly enhanced broadening. So it's not Kerr comb anymore, it's just Kerr broadening, but due to resonance, you can reduce the power requirement significantly.
Okay, any more questions? I have a question, one question. Is material is cost effective so that you can use it as a platform to put everything on, like you said DFB lasers, but no, is it a good, better strategy to put use it as a platform and put everything on the same chip, or is it cost effective to dice it up and use as more like one piece of element?
Yeah, so I mean, we would the way we would envision this depends on application, and it's going to determine how big is each chip, right? Some of these chips can actually be pretty big, right? If you have 2-3 modulators, each is like 2 centimeters, adds up. I mean, that's one drawback of lithium niobate compared to, let's say, silicon photonics. Things are bigger, but are also much lower loss. So we envision that you would do this wafer scale fab in commercial fab, actually, and you would then dice them up and flip chip bond. Actually, make this attach detectors using wafer scale process. I haven't talked much about this collaborative work with Virginia. Dice it up then, and then attach lasers using flip chip bonding where needed. We are looking into also wafer scale bonding for 3-5 materials, but I'm not sure, going back to your question, that this is needed because the scale at the moment that's of lithium niobate photonics needs is probably not as it's similar to 3-5 photonics, right? I wouldn't say it's like as big as silicon photonics at the moment, but we're hoping to get there. So cost-effective material is not very expensive. I mean, like wafer is maybe like $100,000 or something like that. And essentially, once you put it into, the cost goes up, but you can get many devices out of it. So I don't think the material itself is an issue.
Okay. Thank you very much.
Sure.
Any more questions? If not, then let's conclude this webinar. And I would like to thank the speaker for a very interesting, excellent talk. It was so stimulating. So it was very exciting.
Thank you so much.
Thank you very much.
Thank you. Thanks for the opportunity, and have a good night, everyone.
Yes. Good night.